Okay, so this is all on the number e. We started talking about this yesterday. Pi, we said, is about approximately, and they might use that symbol or they might use this symbol for approximately 3.14. 3.14159 is usually the, okay. And E, if you ever forget what E is, remember you can go to the calculator and the E is above the natural log, the ln. If you just go E to the first, okay. Ooh, chirping birds. Birds in the background. Yep, okay. Okay, and that's rounded. Okay, E to the first is approximately 2.718. This E, remember, it's named after Leonard Euler. Looks like Euler, but it's Euler. Okay, and the mathematician, he lived back in 1707 to 1783. Okay, we talked about him a little bit in pre-calc. Okay. E is called the natural exponential function. It's the base for the natural logarithms. In the history, and we did a little bit in this pre-calc, pi is can be expressed as a series. Remember, the series had the plus or minus signs in between. Pi was like 4 times 1 minus a third plus a fifth minus a seventh plus 1/9. You kind of get that pattern. Okay. E, one of the series for E is 1 over 0 factorial. What is 0 factorial? 0 factorial is, by definition, is 1. Remember, 0 factorial and 1 factorial. It's one of the few times that you're going to have two different things both equal to the same value like that. E is 1 over, so when you're looking at this, you're looking at 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and then plus dot dot dot. Show that continues. If you simplify that all out, you're going to get close to 2.718, and then it's going to continue on and on and on. Okay. E to the first is also written as a limit. In the history of math, it's 1 plus 1 over n, that quantity to the n power, as n goes to infinity. Okay. And if you graph, let's graph this in y sub 1. In y sub 1, graph 1 plus, we're going to put in an x instead of an n. We're going to graph this. Okay. 1 divided by x, and then raise that to the x power. So graph that. And we'll just go zoom standard in that. So graph parentheses 1 plus parentheses 1 divided by x, close the parentheses, and raise that to the x power. Okay. And we want to know what happens as the x goes to infinity, as it gets really large or really small in either direction. Do zoom standard zoom 6. And you should see if you drew a little bit less than 3, 2.7. It should be coming on the, okay, something like that, and then it's coming probably starting at 0. Actually, let's do second function calculate value at x equals 0. Where's it starting? It's undefined there. Okay. So somewhere here there's an open, I'm not doing this exact, there's an open circle. Ooh, and it's probably below it, like that. Okay. That's pretty quick. Okay, but if you put the trace key on, okay, and look at the y value, okay, and then say you want to go way out there. So let's change the window. Let's go out to 1,000 and 1,001. X max for 1,000 and X min for 1,001, and then put the trace key on. It should be the y value. Remember, the y value is where the limit's read, and the limit should be getting closer and closer to 2.718. Okay, shows up 2.716. Okay, on our graph. Okay, so the y approaches the 2.718 as a limit. Okay. Now that's looking at the graph for e to the first. Okay. Now e to the x power. Okay, that we did in pre-calc also. It was 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial. Okay, and then plus, and then show 3 dots, plus, and then it's x to the n over n factorial, and then plus dot dot dot. And we did some of those in pre-calc where they had you figure like e to the 0.6 power and did the first 5 terms. And remember, we stored that first, like you'd say 0.65, store that as x, and then type in the first 5 or 6 terms. Okay. Let's graph that e to the x. And zoom 6 is fine. So graph y equals, and the e is right above the natural log, e to the x. And let's do zoom 6. Okay. And it does go through because e to the 0, remember 0, anything to the 0 power is 1. So this should go through 0 and up 1. So this is the graph for y equals e to the x. Now, the next part they go through is what happens on this graph if you draw a tangent line to this curve. What's the first derivative? Remember, tangent lines are the slopes. You figure the slope of the tangent line, that is the first derivative. Okay? So, when they figured the first derivative, okay, this graph of y equals e to the x has a strange property that no other elementary function possesses. A property that no other elementary function possesses. If you place a ruler tangent to y equals e to the x power. Okay, if you place a ruler tangent to y equals e to the x power, you will get the slope to be e to the x power. Okay? So, if we said the function f of x was e to the x, f prime, first derivative, is e to the x. Now, here's the part they left out. It's e to the x, then it's times the derivative of that exponent. So you may want to highlight that. It's times the derivative of x, which would be 1. So that's e to the x. Okay? So the function's e to the x, the derivative's e to the x. What happens if they change that? Let's say I gave g of x was e to the 5x. Then g prime is e to the 5x. It's kind of like the chain rule. Times the derivative of the exponent. Derivative of 5x would be 5. And then they're going to put that coefficient out front. So it's going to be 5e to the 5x. Okay? In terms of general rule, they're going to write it like this. If I said f of x equals e to the u power, then f prime of x equals e to the u, and then times the derivative of u with respect to x. Okay? And that, that you'll need to add to your card. Okay? Except I'm not going to stop now and do it. Okay? We'll come back later and do that. Okay? Okay, now, equations that use some examples. Equations where E occurs. One is the catenary curve. The most famous catenary curve that you know of is the St. Louis arch. Okay? Okay? Another catenary curve, like if you take a suspension bridge, we talked about if you hang a bracelet or a necklace on both ends, a suspension bridge, that's going to be a catenary curve. The St. Louis arch, that's a catenary curve. Looks like a parabola, but it's not. Okay. Form for that might be y equals, this is just a general form, a over 2. And you can look these up on your iPad. Just type in catenary curves. Times the quantity E. We're not going to do anything with these except I'm just trying to give you an example. That's what one catenary curve. Okay. The spiral is another one. You might see some spirals that use E. Spirals that look like this. Okay, and R equals E to the k alpha power. So you might look up spirals. Another one might be the normal curve. Some of you may not experience these in math. You might see them in your science classes. The normal curve's like your bell curve. Remember that in statistics? And that's like y equals 1 over the square root of 2 pi times e to the negative x squared over 2 power. Okay? So you get some really different. Okay? So if you just look up the natural logarithm function, you can find others. Okay. Another, probably one that is used the most in the math, and especially now in the forensic science, growth and decay. When they say, you know, they found a body and the body's been there for 50 years or 200 years, or how do they know this dinosaur came from, you know, thousands of years ago? They're looking at the decay of, usually in humans, it's the decay of carbon. Okay? There's a main formula, and this can be written different depending on your author. Y equals y sub 0 e to the kt power. That kt is an exponent. Okay? That's another one that I would add to your card. Okay? On this, the y is the final amount. The y sub 0, that's the initial amount. The e, for this, they're going to round it to about 2.72. You have to look in the book if the author is using 2.718 or 2.72. The k is a growth or decay constant, so that's like a number. And the t is the time elapsed. They might be talking about the growth of bacteria. They might be talking about the cooling of something. Radioactive isotopes and how they decay. The intensity of light, atmospheric pressure, the decay of sound. There's all kinds of things for growth and decay. Let's look at an example. For a certain strain of bacteria, the growth constant K equals 0.867 when T is measured in hours. How long will it take 20 bacteria to increase to 500? So it's going to grow. Okay? So write the formula down first. Our formula, y equals y sub 0 e to the kt power. Have you done these in physics or chemistry? Chem 2? Nope. Nope. Okay. Okay, so we're starting with 20. That's our y sub 0. We're ending with 500. That's our final amount. For right now, just use E. The growth constant is 0.867, and we're solving for T. Now I'm going to work this two different ways, and then you have your choice which way you like better. First, let's divide by 20. Okay, if you divide that out, you're going to get 25 equals E to the 0.867T. Okay? Okay, and then if I sub in my 2.72 and then 0.867T. Anytime there's a variable up as an exponent, you need to be able to solve it, you take the log of both sides. Okay? Now, I could do log or ln. I'm going to do log. So, take the log of 25 equals the log of 2.72 to the 0.867t power. Third law of logarithms says this goes out front. Okay? So you have the log of 25 equals 0.867t times the log of 2.72. And I'm solving for t, so I'm going to divide by the log of 2.72 on both sides. Okay, so on your calculators, take the log of 25, you got to close the parentheses, divided by the log of 2.72. And I got I'm going to round it 217 for the paper, and it's 0.867t. Divide by 0.867, and my t is going to equal 3.710, and that's in hours. So at that growth constant, it would only take about 4 hours, and you're going to go from 20 bacteria to 500. Okay, which when you're working, you know, the Centers for Disease Control have to know how fast these things grow, and you know, they've got to have some concern on some of those. Okay, now same problem, different method. Okay, draw a little line there. Okay. Okay, so let's start at the 25. I'm going to start at this line. 25 equals e to the 0.867 t power. Okay. If I look at just this 25, I'm gonna go away from this for a minute. 25. If I take the log, natural log of 25, what's understood to be the base? E, and it equals something. Okay. So if I looked at that, it's e to what power equals 25, right? So figure the natural log on your calculator. Do the natural log of 25. Okay, and that's the 3 point. So it's really saying e to the 3.219 equals 25. Okay. Okay, so if I just come up here and take the natural log of this side, I really get the e to the 3.219 equals e to the 0.867t. Bases are the same. Set the exponents equal. Okay, so 3.219 equals 0.867t. So take what's on your calculator divided by 0.867. Okay. And I'm not saying these are the only ways to do this, but these are two. Okay. So if this is in terms of a base e, to get this number in terms of a base e, take the natural log of it. Okay. Now you decide which method you like best. Okay. Okay. Let's look at another example. Okay. In 10 years, the radioactive mass of a 200-gram sample. Oh, I left out the word 10. Sorry. Not sure if I said it. In 10 years, the radioactive mass of a 200-gram sample decays to 100 grams. Solve for K, that decay constant. If it's going from 200 grams to 100 grams, that's its half-life. It went down, it cut it in half. Okay, so in chemistry, probably have already talked about half-life of radioactive elements. Okay, so same formula, y equals y sub 0 e to the kt power. 100 is what we ended with. We started with 200. Okay, and e, k we don't know, and it was 10 years. Okay, so divide by 200. So we're basically down to 0.5 equals e to the 10k power. Solve that for me. Solve for k. Compare your answers. What's that? On. Press on the brake key. Sometimes you press enter is pause on the brake. Yeah. To get a negative value, should negative 0.069, is that close? Okay. What'd you do to figure it? natural log of 0.5 and then set the exponents equal. Okay? Did the first way. Okay. And I don't care which method you do it. Okay? Okay. But you should get a negative 0.069, and that's the decay constant. Okay? Okay. That's a little bit about E.